All right, here's example 15.14 out of Hibbler, and we're going to walk through this um, problem as an example, angular momentum, and there's also a work piece of this. But so a 0.8 pound ball B, shown in this figure, is attached to a cord. So here's B here. It's attached to a cord that goes through the table. There's a hole in the table right here. So this cord on B goes to that hole, then goes down under the table, and then some invisible hand is down there pulling on that cord. So it's going to make the ball get closer, and you can see this pathway here gets closer and closer and closer until eventually, the ball will hit the hole. So anyway, the cord is being pulled. When the ball starts, it's at 1.75 feet from the hole, and it's going around in a circle. So there's not yet a pull on the cord. It's going around in a circle such that its speed is 4 feet per second. And then this force is applied, and what happens is it creates a constant speed. It's called V sub c, but really it's C for constant, but it's also a radial change in position. So 6 feet per second that cord is being pulled down here, and that's going to cause a radial motion. If it wasn't spinning, it would just straight to the hole at 6 feet per second. All right, so what we need to do is find the speed of the ball when r is equal to 0.6 feet. So as drawn here, we'll call this that point, 0.6. And so that's kind of, we can use angular momentum to get there. We have an angular momentum to start with. We know the r, the radial length, and we know the speed 4. So we can get the initial angular momentum, and then we can get the final because we have the r distance in that case too. So let's work on A, but real quick we'll write down what out of B. We need to find the amount of work done by the force F in shortening the radial distance. So there's a work. Work. All right, so there's this force is applied over some distance, and in this case the force is down and the distance is down, so it's just going to be F times, actually we know it, 1.75 minus 0.6, so 1.15 feet is the distance. Unfortunately, we don't know the force, so what are we going to do with that? So we may also have to look at the work done from position 1 to position 2 is also going to be FDS. So we may need to use that as a way of figuring out the force, but we'll come back to the work piece. Let's get this speed piece first. So I'm going to zoom this in a little bit. All right, so what do we know? We know that if we pull out our momentum equation, that the initial angular momentum plus an impulse, sum of moments over time, is going to equal the final angular momentum. Now let's look closely at the situation, what we have going on here, and Hibbler drew for us this nice chart, graph, whatever you want to call it. And so as you come around, the only force is, it's the normal and the weight forces that offset each other. So these two just keep the ball from going up and down, stays on the surface of the table. And then the force is from the cord pulling towards the hole, towards the center of the table. Now, what you notice about the force is it is always in the direction of the r vector. If this is r here, and there's a force this way, force is in, r is out. True over here too. The force is always in in the opposite direction of the position vector. And so when you have a cross product of two vectors that are either in the same direction or in opposite directions, the sine of that angle between them is 0. So there is no moment from these forces felt by this particle. So we can simplify this equation then, setting this term to 0, and so we're left with the initial angular momentum equals the final angular momentum. So R cross mv1 equals R cross mv2. All right, so what we have at the very beginning, the R and the V is 4 and the R is 1.75, and they're 90 degrees to each other. So this initial term is 1.75 feet times the mass of it, 0.8 pounds, times that initial speed, which is 4 feet per second, and it's going to equal R2 is 0.6 feet, so 0.6 feet crossed into mass, 0.8 pounds, and then V2. So this 0.8 will cancel. I don't even have to do math with it. So V2 equals 1.75, because the feet cancel, divided by 0.6 times 4, and that's in feet per second. So that answer is 11.67. But you have to be careful. What is V2? What did we just calculate as V2? We calculated the angular momentum. So this term, it's only the component of speed that is perpendicular to the radius. So if you look at this piece over here, we just calculated that term. There is another component which we know that's tending to come in that has nothing to do with the angular momentum, right? So we got to keep that in mind. So that's only part of the equation. There's another, so as Hibbler calls it, V prime 2, and then we know that V, the radial, as defined as in, I'm defining radial as in positive direction, is 6 feet per second. So our total velocity of the ball at 2 is the square root of 6 squared plus 11.67 squared, for an answer of 13.12 feet per second. So I kind of glossed over it, but R cross mv2. So another way to write that would have been R mv2 sine theta, and so we could have done this using trig, although finding that angle would have been challenging. So I just determined, actually what I actually did, to be clear, is I said R m v2 tangential is what we ended up calculating, and then we used the radial here to get the full complete picture. So keep that in mind. All right, so there's our answer to velocity of the ball at 0.6 feet, is that. All right, so the second part of the problem, we want to know the work, and as we said, the force, and nothing we determined over here would give us a force. So if we want to calculate, if we want force as a function of S, So what we're going to need if this is going to work, we know that that wouldn't be m times acceleration in the radial direction, because the force is only going to be in the radial direction. So we can simplify it to acceleration radial, and we can say that that's velocity squared over the radius. But now I need speed as a function of radius. I don't have that either. So let's pause this and let's look at U1 to 2. Let's use energy. So if I say that the kinetic energy initial plus the sum of work from 1 to 2 is going to equal the kinetic energy final. Can I do that? So, well, yeah, I know initially that the speed, so 1/2 mass times 4 feet per second squared plus, and there's only one work, there's no friction, the gravity's in the wrong direction, so I'll just call it U, that's the work. And that's going to equal 1/2 mass times at time 2, it's 13.12 feet per second, running out of space, squared. Right, so the work done from 1 to 2 is going to equal 1/2 of mass times 13.12 squared minus 4 squared feet per second, feet squared per second squared, actually. So what that comes out to be is 1/2 of 0.8 pounds, and we need that to be over 32.2 feet per second squared times feet squared per second squared. I'm just moving this here. And then these terms, 13.12 squared minus 4 squared, for an answer of 1.933 pound-feet. So that's how you get the work. Again, this is another case where conservation of energy saved us from some ugly math trying to figure that out. So anyway, that's that problem. Thank you. Any questions, hit a comment down below, or bring it to class. Thanks.